Okay, so we're going to go ahead and start talking about factoring polynomials. But the first thing we have to do is talk about factorizations, breaking down numbers. So the whole numbers that are multiplied to find a product are called the factors of that product. So we're talking about whole numbers that are being multiplied. A number is divisible by its factors. So the order of the factors does not change the product. So for example, we have the factorizations of 12. We've got 1 times 12, 2 times 6, 3 times 4, 1 times 4 times 3, 2 times 2 times 3. Now why is 2 times 2 times 3 circled? Well, that is what we call our prime factorization, because all the numbers we are multiplying together are what we call prime numbers. So even though there's multiple ways to factor a number, when we want it broken down into just prime numbers, then that would be our prime factorization. Now these numbers can be written in any order. And other than the changes for the order, there's only one way to write the prime factorization. So I could have rewritten this. This is my prime factorization. It could have been written 3 times 2 times 2, 2 times 3 times 2, but it's still just those numbers being multiplied together. So there's a unique prime factorization for every single number. And everyone's prime factorization will be different, every number's. Now, to be able to do prime factorization, you have to know your prime numbers. And most people think that 1 is a prime number, but it is not. It's one of our special cases. It's not truly prime. And so the main prime numbers you need to know are the 2, 3, 5, 7, 11, 13, 17, so on and so forth. So it keeps going forever and ever. So now the question is how do you find the prime factorization of a number? Now there are two methods. There is the tree diagram, which some people really love. A lot of elementary school teachers teach it. A lot of middle school teachers teach it. I don't like it. I think it's too messy, but I have no issues if that's the way you want to do prime factorization. It's nice because it allows you to just go ahead and say, okay, 4 times 12 is 48. So your numbers don't have to be prime for a tree diagram. Where our second method, reverse division, they have to be prime numbers. And then you just keep breaking it down. Well, 4 is really 2 times 2, and 12 is really 3 times 4, and 4 is really 2 times 2. And then all those little n's are your prime factorization. So I've got a 2, and a 2, and a 3, and a 2, and a 2. Why I don't like this is because it's easy to go, oh yeah, here are my numbers, and totally forget about the 3, because it's messy and unorganized. And so if I have a tendency to forget a number every 3 problems, I'm going to get so much of it wrong that it's not worth my time to use that method. So this is why we have a reverse division method. We start with our original number, and then we do a division symbol like this, which is slightly different than our normal division symbol. I get it. And we start with our lowest prime number, 2. And when I say, okay, can 2 go into 48? Okay, 2 goes into 48, and it goes 24 times. And I keep using 2 until I can't anymore. So 2 goes into 24 12 times. Now the thing with this one is these numbers have to be the prime numbers. So you have to know your prime numbers. And then 2 goes into 12 6 times. And then 2 goes into 6 3 times. And 3 is prime, so I stop there. And what's nice about this is it gives us every number in order. 1, 2, 3, 4. And there's our prime factorization. Now some people do prime factorization in exponential form, so that way you're not writing as many 2's, which is totally okay. It still represents the same thing. So sample problems, find the prime factorization. So 16, I'm going to go ahead and break it down my method. So 2 goes into 16 8 times, 2 goes into 8 4 times, 2 goes into 4 2 times, and I stop because 2 is prime. So now on the outside here, I have all my prime numbers. So 2 to the 4th power, or 2 times 2 times 2 times 2. Okay, next one's a special case, 15. So when I break down 15, 2 doesn't go into 15, but 3 goes into 15. So I start with my first prime number 2, it doesn't go, so I move to my next prime number 3, and 3 goes 5 times. So my prime factorization is just 3 times 5, and that's it. And then our next one, 3, which is prime in itself, so its prime factorization is just itself, 3. And that's prime factorization for you. Again, you don't have to use my reverse division method. If tree diagram works for you, that's fine. Just make sure that you're consistently correct with your answers. Okay, factors that are shared by 2 or more whole numbers are called common factors. The greatest of these common factors is called the greatest common factor, or GCF. And we use prime factorization to find the GCF of any 2 terms. So when I'm looking at numbers 12 and 32, I can actually use the prime factorization for 12. So 12, 2 goes 6, 2 and 3. And then I can look at 32. Okay, 2 and 16, 2 and 8, 2 and 4, 2 and 2. And then to find the greatest common factor between them, I look at all the primes that are common between them. So they each have a 2. They each have another 2. And that's it. So they both have 2 2s, which means that my greatest common factor is 4. Now, some people can do this without breaking down into greatest common factors, and that's fabulous if you can do that. But you have to be able to do it consistently. So this is just a method for those people who are like, I have no idea. So we can break down 24, 2 and 12, 2 and 6, 2 and 3, and I can break down 18, 2 and 9, 3 and 3, and then I look at where my common factors are. So they each have a 2, they each have a 3, so my greatest common factor is 2 times 3, which is 6. Now that you look back at 24 and 18, you can be like, oh yeah, I see where that's 6. That makes sense. Now we can also do this with polynomials. So 15 is really 3 times 5. Let me rewrite that so it doesn't look so weird. So 15 is 3 times 5, and then we have 3 x's. Now 9 is really 3 times 3, and then I have 2 x's. So then I can go ahead and say, okay, what do I have in common? I've got some 3's, I've got some x's, so my greatest common factor is 3x squared. And again, some people can look at it and just figure it out, but this is giving you a method. So let's see, 8 is 2 times 4, 4 is 2 times 2, 12 is 2 times 4, no, 3 times 4, and that 4 is 2 times 2, 1, 2, 3, 1, 2. And then again, we look at what's common between them. So let's look like we have some 2's, got some x's, we've got a y. So that means my greatest common factor is 2 times 2, which is 4. We've got 2 x's in common and 1 y in common. And so we're going to use these last 2 examples to kind of talk about, you know, this little helpful hint that if 2 terms contain the same variable raised to different powers, the greatest common factor of that variable is going to be the lower power. So if we look up here, I have an x to the third and x to the second. My greatest common factor has an x to the second because it's a lower value. And then when I'm looking here, x to the second and x to the third, x to the second. Y to the first, y to the second, I have a y to the first. So that's just a helpful little hint for you when you're dealing with variables. So you don't have to write out all of those factors each time. So when I'm looking at these, again, you can break them down using prime factors, or I could say, okay, these, let's see, 9, they both have 9 that go into them. This one has 15, no, that one doesn't, that one has 12. 12 doesn't go into there. So 9 is a common factor, and then they each have an x, and the lowest exponent is 2. They both don't have a y, so y is not a common factor. And again, you could break those down and do that same sort of thing. So you can say a 36, 2 and 18, 2 and 9, 3 and 3, and then 45. 2 doesn't go into there, but 3 goes 15 times. 3 goes into 15 5 times. Okay, I've got 2 3s and 2 3s. So the greatest common is 9. And then you can look at x, 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 y, y. What do they have in common? 2 x's, and get your answer this way. So again, lots of different options to you, just trying to show you different ways to make it a little bit quicker. So let's see, 12 and 28. So their greatest common factor is 4. And then I have an x and an x to the third. So this is an x to the first. They both have x's, so they're going to share an x. And the power is going to be the lowest of the two, which is the first power. So 4x would be our greatest common factor. So that's what we're going to work on in class. I wish you luck, and I'll see you